Welcome to the Deep Dive. Today, we're really tackling something fundamental, core programming stuff.
Yeah, we're talking data structures and algorithms.
Exactly. How we organize data, how we work with it efficiently. You sent over some great material, including bits from Bhagwan Kamadi's book on doing this with Golang.
Right, learn data structures and algorithms with Golang.
And our mission, really, is to pull out the key ideas for you, make it accessible.
We want to get you straight to the heart of how software actually handles information, behind the scenes.
Right.
It's the building blocks.
Okay, so the book kicks things off by classifying data structures. Lots of categories here.
It's a good starting point. Helps get your head around the landscape.
We've got linear ones first, things in sequence, like lists, stacks, queues. Simple enough.
Straight line, basically.
Then nonlinear, more complex connections, trees, graphs.
Yeah, where things branch out or link up in all sorts of ways.
It also distinguishes between homogeneous holding all the same kind of data, like arrays,
Right, all integers or all strings.
and heterogeneous, which can hold a mix. Linked lists were mentioned there.
Which gives you flexibility.
And finally, dynamic structures, the ones that can change size while the program's running.
Super important. That adaptability. It's quite a range, actually.
It really is. And knowing these types helps you choose the right tool for the job right.
Absolutely. It's the first step. What kind of organization does my data need? That's the question you start asking yourself.
Now, interestingly, before diving deep into lists or trees, the book starts with structural design patterns.
Yeah, these are like blueprints, reusable solutions for common software design problems, how you put the pieces together.
Right, it listed quite a few. Adapter, bridge, composite, decorator, facade, flyweight, private class data, and proxy.
It's a lot to list off, but the core idea is about how objects and classes work together to build bigger, more flexible systems.
Okay, let's maybe touch on a couple. Adapter. Sounds like making things compatible.
Exactly. It helps interfaces that weren't designed for each other to, well, cooperate, like a travel adapter for your plugs.
Gotcha. And bridge. Decoupling abstraction from implementation.
Yeah, so you can change the high-level idea or the low-level details independently. Think of like having different shapes, abstraction, and different ways to draw them, maybe using different graphics libraries, implementation. Bridge keeps those separate.
Makes sense. Composite sounded interesting too, treating individual objects and groups of objects the same way, like files and folders.
Creates those tree-like structures. Very useful for hierarchies.
And decorator, adding responsibilities dynamically.
Yeah, like adding extra features on the fly without changing the original object's code. Think adding scrolling to a text view. The view itself doesn't change, you just wrap it in a decorator.
Facade seemed pretty straightforward, a simplified front end to a complex system.
Totally. Like the ignition in your car hides all the engine complexity, you just turn the key.
Okay, flyweight was about efficiency, right? Sharing object state.
Yeah, for when you have tons of objects that share some common data, saves memory by sharing that common part, like character rendering in a text editor.
And private class data, well, that sounds like encapsulation. Keeping things secure.
Pretty much. Basic object-oriented principle.
Proxy then acts as a stand-in, controlling access.
Right. Could be for lazy loading, access control, logging, lots of uses. It intercepts requests to the real object.
So these patterns are really about building robust, maintainable code. Good tools to have in your belt.
Definitely. Recognizing them helps you understand existing code and design better new code.
Okay, shifting gears. Algorithm analysis. This is where we figure out how good an algorithm is.
How efficient.
The book focuses on complexity, how performance scales with more input data. And performance itself, like CPU time, memory usage.
And this is where big O notation comes in, right?
Yes, big O, the classic.
It's absolutely key. Gives you a language to talk about how runtime or memory grows. OM, linear. Double the input, roughly double the time.
Like searching a list one by one.
Exactly. Then you have things like O log n, logarithmic, much better, like binary search and a sorted list. Doubling the data adds only a tiny bit more work.
Super efficient.
And then O and n, quadratic. Get slow fast. Double the input. Time quadruples. Some simple sorting algorithms are like this.
Right. And the analysis isn't just one number, is it? The book mentions worst case, best case, average case.
Yeah, and amortized complexity too.
So like the absolute slowest it could be, the fastest possible, what usually happens.
And amortized is like the average cost over a whole sequence of operations. Sometimes one operation is slow, but it averages out nicely.
Gives you a fuller picture of the performance.
Definitely. You need to consider these different cases depending on what you're building.
Okay, then we got a quick tour of algorithm types, broad categories.
Like different strategies for solving problems.
Brute force, simple, maybe slow, try everything.
The straightforward approach. Not always elegant, but sometimes it's all you need for small problems.
Divide and conquer, break it down into smaller pieces.
Classic. Think merge sort or quick sort. Solve the small pieces, combine the results.
Greedy algorithms make the best choice right now. Locally optimal.
Yep. Hope that leads to a globally optimal solution. Doesn't always, but works for some problems, like finding minimum spanning trees.
Dynamic programming solving overlapping subproblems efficiently. Sounds complex.
It can be tricky to wrap your head around, but it's powerful. Avoids recalculating the same thing over and over by storing results. Think Fibonacci sequence calculation, the efficient way.
Right. And finally, backtracking. Trying possibilities and backing up if they don't work out.
Like exploring a maze. Hit a dead end. Turn back and try another path. Good for solving puzzles or constraint satisfaction problems.
Like a whole toolbox of approaches.
Exactly. Knowing these patterns helps you figure out how to attack a new problem.
Okay, now we get to the Go specifics. How do we actually do this stuff in Go?
Right. Connecting theory to practice.
So arrays and slices are mentioned.
Right.
Creating them, using append, copy, the basics of ordered collections in Go.
Slices are built on arrays, but are more flexible. You'll use slices constantly in Go.
Then maps for key value storage. Super useful.
Absolutely. Go's maps are hash tables underneath. Very fast lookups.
Structs for defining our own custom data types.
Essential for modeling your data properly.
Channels were mentioned for concurrency, but maybe not explored deeply in these parts.
Yeah, channels are huge in Go for communication between Go routines, but seems like the focus here was more on the core data structures themselves.
Got it. Also, functions variadic ones, deferred calls, defer, and error handling with panic and recover.
Standard Go features, but important context for implementing algorithms. Defer is particularly neat for cleanup actions.
And it gets really practical, showing database interaction with the squalid package. My simple examples for CRE operations.
Create, read, update, delete. Yeah, showing how to connect, run queries, insert data. Basic but essential stuff.
That's connecting the dots to real applications.
And it highlights Go's standard library. The squal package gives you a consistent way to talk to different SQL databases.
It even touched on basic web forms with Nest TDP and text template. Simple CRM example.
Again, showing Go's capability for web development right out of the box. Nest TTP is very powerful.
Okay, let's dive into the specific data structures, starting with linear ones. Lists first.
And the focus seems to be on linked lists.
Yeah, singly and doubly linked. How nodes connect with pointers, adding nodes, finding the end, inserting.
Linked lists are fundamental. Different trade-offs compared to arrays or slices. Great for insertions, deletions in the middle, not so great for random access.
Then sets. Implemented using Go maps, apparently.
Yeah, that's a very common and efficient Go idiom. Use the map keys to store the set elements. The value can just be a Boolean true or an empty struct.
Operations like add, delete, check existence, and finding intersection and union. Makes sense with maps. Fast lookups.
Exactly. Hash table performance for membership testing.
Tuples got a quick mention. Finite ordered sequences. Fixed size.
Yeah, Go doesn't have a dedicated tuple type like Python, but you can achieve similar things with structs or sometimes just multiple return values from functions.
Queues next. First in, first out. FIFO.
The waiting line principle.
And the example used Go channels and Go routines for synchronized queue. Ticket issuing simulation.
That's a great Go-specific example. Using channels naturally handles the synchronization needed for concurrent access to the queue. Very idiomatic Go.
Lastly, for linear, stacks. Last in, first out. LIFO.
Like a stack of plates.
Implemented using slices. Push to add to the end, pop to remove from the end.
Simple and efficient with Go slices. Appending and slicing off the end are fast operations.
Okay, moving to nonlinear structures.
Yeah.
Trees are up first. Specifically, binary search trees, BSTs.
Right. Nodes with at most 2 children, left and right, and that crucial ordering property.
Everything in the left subtree is smaller than the node. Everything in the right is bigger.
That's what makes searching fast O log n on average. You can eliminate half the tree at each step.
Operations covered. Insert, search, find min-max, and traversal methods in order, pre-order, post-order.
Different ways to visit all the nodes, useful for different tasks. In order gives you sorted elements from a BST.
The notes mentioned other trees like AVL, B trees, and the code, but not detailed here.
Yeah, those are more advanced self-balancing trees that guarantee the O log n performance even in the worst case, which a simple BST doesn't. Important for real-world use.
Then, tables. A basic table structured with rows and columns. Pretty literal.
A simple way to represent tabular data, like a mini spreadsheet structure.
Symbol tables were mentioned briefly, used in compilers.
Exactly. Compilers use them to keep track of variable names, function names, their types, scopes, all that stuff during translation. Basically a dictionary for the compiler.
Okay. And then containers. It mentioned Go's container package.
Yeah, which gives you ready-made implementations of heap, list, doubly linked, and ring, circular buffer.
And it also pointed out that built-ins like maps and slices are containers too.
Right. Go provides containers both through built-in types and the standard library package. Hash functions like SHA-256 were mentioned here too.
Right, for integrity or maybe used within some container implementations.
To be. Hashing is fundamental to things like hash maps.
Let's talk homogeneous structures now. All the same data type. Matrices are the big example. 2D arrays.
Yep. Rows and columns.
Creating them, accessing elements, basic operations, add, subtract, multiply, transpose. Standard linear algebra stuff.
Crucial for graphics, simulations, machine learning, lots of areas.
It also listed different matrix types. Row, column, triangular, null, zero.
Specific structures that have useful mathematical properties or allow for more efficient storage or computation in certain algorithms, like only storing the non-zero parts of a triangular matrix.
And then some fun ones. Zigzag and spiral matrix traversals.
Good exercises for practicing array manipulation and controlling nested loops. Gets you thinking about indexing.
Multidimensional arrays, and tensors got to mention too, with an example of unfolding a 3D array.
Stepping beyond 2D. Tensors are basically the generalization of vectors and matrices to higher dimensions. Hugely important in machine learning and data science.
Think like a cube of data, or even more dimensions. Unfolding is like flattening it out in specific ways for processing.
Precisely. Reshaping data is a common task when working with tensor libraries.
All right, heterogeneous structures. Holding different data types. Linked lists came up again.
Yeah, reinforcing their flexibility. Since each node is separate and just holds data and pointers, the data in each node can be of a different type if needed.
Circular queues were introduced too, and connects back to the beginning.
Like a ring buffer. Useful for fixed-size buffers where you want to overwrite the oldest data when it's full. Efficient reuse of space.
Then ordered lists, focusing on sorting in Go, using the sort package.
Very powerful package.
It showed using sort. Sort by implementing the len swap less interface methods on your custom types.
Right, sorting employees by age or things by whatever criteria you define in less.
And also sars, slice, which often feels a bit easier using anonymous functions for the comparison.
Yeah, especially for simpler sorts or sorting based on just one field. Very convenient.
The multi-sorter example looked really useful sorting by multiple criteria, like commits by user, then language, then lines of code.
That shows the real power in composability. You can chain sorting criteria together. Very cool.
Unordered lists got a brief nod, mainly related to HTML's alt tag.
Yeah, in data structure terms, it often relates more to sets or hash maps where element order isn't guaranteed or the primary concern. It's about membership or key-based access.
Okay, dynamic structures, things that resize. Dictionaries or maps in Go are key here.
Absolutely. They grow as you add things.
Lots of methods covered. Put, remove, contain, find, reset, number elements, get keys, get values, the whole CRUD plus extras for maps.
Standard dictionary operation.
And importantly, using sync.rw mutex for safe concurrent access.
Crucial in Go. Since maps aren't inherently safe for concurrent reads and writes, you need mutexes, like RW mutex, which allows multiple readers concurrently, to protect them if coroutines might access them simultaneously.
Tree sets were mentioned. Sets implemented using trees.
That's the idea. You get the uniqueness of a set, but because it's tree-based, likely a balanced BST, you also get efficient ordered traversal and operations that maintain sort order. Best of both worlds sometimes.
Interesting. And then sequences. Mathematical ones.
A bit of a diversion, but cool examples of generation.
Fairy sequence, reduced fractions. Fibonacci, recursive and iterative. Look and say.
And Thumors, based on Boolean complement. Fun algorithms to implement, shows how code can generate these patterns.
Right. Now for some classic algorithms deep dive. Sorting first.
The greatest hits.
Bubble sort, selection sort.
Simple, slow, ON. Good for learning, not usually for production on large data.
Insertion sort mentioned. Shell sort.
Insertion sort is also ON, but better on nearly sorted data. Shell sort is an improvement on insertion sort faster.
And then the heavy hitters, merge sort and quick sort.
Both generally ON log n, much faster. Merge sort needs extra space. Quick sort is often faster in practice, but has a worse case ON, though rare with good implementations.
It's a whole spectrum of sorting techniques with different trade-offs.
Understanding these is fundamental. You need to know why you'd pick one over another.
Then searching. Linear search, simple ON. Binary search, needs sorted data, O log n.
Big difference in performance on large sorted data sets.
And interpolation search. An implementation was shown for that one.
Yeah, it's like binary search, but tries to make a smarter guess where the element might be based on the values at the ends. Can be faster than binary search if data is uniformly distributed, but worse otherwise.
Recursion came up again. Function calling itself.
Mentioned with divide and conquer and Fibonacci. Elegant, but watch out for stack depth and potential performance overhead compared to iterations sometimes. Need that base case.
Hashing also revisited, using crypto SHA-1 and Go. And an assorter function to combine hashes.
Hashing is everywhere. Maps, crypto, data integrity. SHA-1 is shown, but yeah, often needs stronger ones like SHA-256 now for security. XOR is a simple way to combine multiple hashes into one.
Okay, next section. Network and sparse matrix stuff. Graphs first.
Modeling connections, nodes and edges.
Concepts like directed, non-directed, connected. Representation using an adjacency list. Social graph example.
Adjacency list is common for sparse graphs. Graphs with relatively few connections. Efficient storage. Just list the neighbors for each node.
Methods like addLink, printlinks. Another example with name entities. Very flexible way to model relationships.
Absolutely. Social networks, roadmaps, dependencies. Graphs are everywhere.
Knowledge graphs were also introduced. Knowledge graph struct, class entities, links.
More structured. Defining types of entities and relationships. Big in AI and semantic web. Representing knowledge so machines can reason about it.
And sparse matrices. For matrices with mostly zeros.
Crucial for efficiency when dealing with huge sparse data sets.
The implementation used a list of lists, LOL type, to store just the non-zero cells and their coordinates, plus the overall shape.
Avoid storing and processing millions of zeros. Methods like getValue, setValue work with this sparse representation, common in scientific computing.
Finally, memory management, always important.
Especially in a language like Go with automatic garbage collection.
Yeah, the book covered garbage collection. GC. Overview of automatic memory management, different algorithms mentioned, reference counting, mark and sweep, generational GC.
Different strategies the runtime uses to find and reclaim memory that's no longer needed. They have different performance impacts, like pause times.
The reference counter example showed one basic approach. Performance considerations are key with GC.
Right. Ghost GC is generally very good, but understanding it helps write efficient code and tune it with things like GeoGC if needed.
Cache management was next. Implementing a simple cache with cache object having a value and time to love it, TTL.
Caching is all about performance. Store frequently accessed stuff in faster memory to avoid hitting slower storage, disk, network repeatedly. TTL helps keep the cache fresh.
Methods like getObject handling expiry, setValue, basic but fundamental caching logic.
Essential technique for speeding up applications.
And last bit, space allocation. Stack frames, pointers and Go. Simple add-in pointer example.
Understanding the stack for function calls, local vars, versus the heap for dynamically allocated data that lives longer. Pointers let you work with memory addresses directly.
Also mentioned Go's built-in GC again, and optimization best practices. Ties it all together at a lower level.
Knowing how memory works helps you write code that uses it efficiently. Avoid unnecessary allocations. Understand pointer usage.
Wow, okay, that was a lot. We covered a huge amount of ground.
It really was a deep dive. From basic classifications and design patterns right through specific Go implementations, algorithms, and memory.
Data structures. Linear, nonlinear, homogeneous, heterogeneous, dynamic. Algorithms. Sorting, searching, hashing. Representations for graphs. Sparse matrices. Memory management.
Hopefully that gives everyone a much clearer picture of these core CS concepts and how they play out in Go.
So what are the big takeaways here? For me, it really hits home how choosing the right data structure is so critical for performance.
Absolutely. A hash map versus a sorted list for lookup, night and day difference with large data.
And those design patterns aren't just theory. They really help structure your code for the long haul, make it maintainable.
Yeah, they provide proven solutions. And memory management, especially GC versus manual, that choice impacts everything depending on your application's needs.
Even those math sequences, like Fibonacci, pop up in unexpected places in computing.
It's all interconnected. Structure affects algorithms, affects performance, affects design.
So for anyone listening, the world of data structures and algorithms is massive, right? But these fundamentals are the key.
Definitely. We encourage you to dig deeper into areas that caught your interest. Maybe compare sorting algorithm complexities in detail.
Or look into real-world graph applications, social networks, mapping.
And the best way to learn is to code. Try implementing some of these things yourself in it all. Break them, fix them, understand them.
Get your hands dirty, there's no substitute.
Not at all.
Okay, final thought to leave you with. We're drowning in data, right? It's growing exponentially. How will the constant evolution of data structures and algorithms, things may be optimized for AI, for massive data sets, how will that shape the future? What problems will we be able to solve tomorrow that we can't today because of these advancements?
That's the big question. It's a field that's constantly pushing boundaries because it has to. It underpins so much technological progress.
Something to think about. Thanks for taking this deep dive with us.